This is another example of static rotational equilibrium. So what we have here is a solid disk. The center of it is centered on this frictionless axle. A force of 8 newtons is applied leftward to the outer edge of the 2 kilogram solid disk, 0.2 meters from the axis of rotation. Another force, F sub B, standing for the force at the bottom, is also applied leftward 0.12 meters from the axis of rotation, such that the system does not move. All right, so let's use our second law linear and translational toolkit for a system that's in static equilibrium. First, let's determine the accelerated system. In this case, it's a solid disk. Well, let's determine the coordinate system. As usual, we'll say to the right is positive and counterclockwise is positive. We're going to draw our force diagram and motion map. So because it's in static equilibrium, in other words, nothing's moving, horizontally or both horizontally and vertically, actually in any linear direction, the linear acceleration and linear velocity are both 0. In the rotational direction, both the rotational velocity and the rotational acceleration are also 0. Now let's look at the forces. So we've got a normal force vertically because the solid disk sits on something at the center. So whatever it's sitting on is pushing upward from the center and upward. The force due to gravity is pulling down. We always draw that relative to the center of mass. Now, we were told that there are these two forces, the force of tension at the top and the force of tension at the bottom. If those two forces really do exist, like the problem tells us, and we don't have some other force balancing it out, like this horizontal normal force, then the system would move to the left, according to Newton's second law. So, therefore, something has to be balancing this out. And so we have to include this horizontal component of the normal force. All right. Let's explicitly write out the Newton's second law in the horizontal and vertical and the rotational Newton's second law equations. So there they are. The sum of the forces equals mass times acceleration. Again, because nothing's moving, that equals 0. And we should always say that the sum of the torques also equals 0. So let's first start off with the vertical. So the sum of the forces in the vertical should equal 0. And our two vertical forces are the vertical component of the normal force and the force due to gravity. They add up to 0. We know how to solve for the force due to gravity. We know the mass of this object is 2 kilograms, so we multiply that times 9.8. That gives us negative 19.6 newtons. The normal force, therefore, must also be 19.6 newtons, but positive because it's upward. So these two forces must be balancing each other. In the horizontal, we've got Fnx, the horizontal component of the normal force, and the force of tension at the top and the force of tension at the bottom. They have to all balance out to equal 0. We're told that the force of tension at the top is negative 8 newtons. That's given to us in the problem. So here are a few things that we already know. The force due to gravity, F and Y. Now let's look at the torque. The sum of the torques we said was equal to 0. So the torque from the force of tension at the top minus the torque from the force of tension at the bottom, they should add up to equal 0. Notice we didn't include any torques from the normal force in the vertical, the normal force in the horizontal, and the force due to gravity because they all go through the axis of rotation. Therefore, if we were to calculate them, their R's would be 0. Okay, so let's calculate the torques for the force of tension at the top and the force of tension at the bottom. The force of tension at the top we know is 8 newtons. That's given to us. And the distance from here to there is 0.2 meters. We're told that the radius is 0.2 meters, so that's where this force of tension is being applied. There's essentially a string pulling it that way. We're going to subtract the force of tension from the bottom times the distance that it is being applied to the center of rotation. So in this case, that gives us a torque for the force of tension at the top of 1.6 Newton meters. And the force of tension at the bottom, we've got to calculate that. Well, since we know from up here that the two of them added together should equal 0, the force of tension at the bottom should be negative 1.6 Newton meters. So if we rewrite this equation and plug in what we know, we end up with this equation here. We're told that this force of tension at the bottom is applied at a location 0.12 meters from the axis of rotation. So all we have to do is solve this equation for the force of tension at the bottom, and we get 13.3 newtons. Now, let's convert that to the force of tension in the horizontal and vertical direction. So we calculated out to be 13.3 newtons using this equation, but we were looking at it rotationally. When we convert it back into the horizontal world, because that force of tension on the bottom is pointing to the left, we need to make sure we include that negative sign there. So these are all the values that we've calculated so far. All right, now there's still some things horizontally we haven't calculated out. So let's go back to our horizontal equation. We need to solve for Fnx. We're given F, the force of tension at the top, and we've just recently solved for the force of tension at the bottom. So this equation, when we plug in FTT and FTB, we get this equation, so we can find the horizontal component of the normal force. It's 21.3 newtons. So if the horizontal component of the normal force is 21.3 newtons, and that's the net rightward force, that's this force here, then there must be a net leftward force of these two forces pulling with a force of negative 21.3 newtons. Those two together pulling in the opposite direction. All right, and finally what we have to do is solve for the rotational inertia. So the rotational inertia of a disk is just 1/2 mr squared. They give us the mass of 2 kilograms, the radius of 0.2, and that becomes 0.04 kilogram meter squared.